Okay, good morning, everyone. So if anyone has questions about AC power factor correction, please ask now. No one? Okay. All right, well, let's get started. Let me put this on silent. I thought I had. Okay, I have double-digit attendance. I'm happy, actually. I walked by a few classes this morning and, well, there's like 10 students in one, there's like 12 in another. There's like 4 students in one 8 a.m. class. Zoom, I have, let's see, how many do we have? It's about 8 on Zoom. So yeah, double digit. But 50% attendance. All right, we'll begin with chapter 6 today. Chapter 6. So let's go here. It's triggered 321. And 1. Chapter 6. Frequency response. So this chapter again uses complex numbers. Okay, so we'll be working with in terms of like omega and frequency F. Now, the title of the chapter is frequency response, but the circuits we study in here are basically filters, like electronic filters. Now, this table right here displays the most common frequencies of the signals that we have, that we use in everyday life. Okay, and I've talked about this before too. We are surrounded by electronic signals that have like variations in frequency all the way from tens of hertz all the way to like megahertz, gigahertz, and even terahertz, right? Each one of these signals, whether they are wired or whether they are wireless, transmits at a particular frequency. And so if you have 2 or more signals transmitting at the same particular frequency, it is going to cause interference. Any signal that we don't want in our circuit is referred to as noise. So electrical noise is basically something that is unwanted for the purposes of our circuit or functioning of a circuit. So to prevent interference or to prevent noise signals from coming in, we use electronic filters. Like a mechanical filter, an electronic filter blocks out certain signals and it only allows certain signals to pass through. Okay, so for instance, take FM radio stations or AM radio stations, right? Each of the numbers for those radio stations is the broadcasting frequency, meaning 99.7 megahertz, 99.7 FM has to do with the broadcasting frequency, which is 99.7 megahertz. So if you're tuning your radio station, what you're doing is there is a tuner at the front end. You're setting the frequency that is going to be accepted in the FM radio as 99.7. There's also a filter. The filter at the front end of every device is only going to allow that particular frequency to come in. If you want 99.7, it's only going to allow 99.7 to come in. Everything else is blocked out. Okay. Same thing with the cellular phone signals. You have AT&T, T-Mobile, Verizon. All of those operate at certain frequencies, and they operate with what is known as frequency bands. Okay. And so there's a filter at the front end of every wireless device. So every smartphone has a filter at the front end. So let's look at what filter is. But before we talk about filters, I want to present a 2-port network. 2-port network essentially is the same circuits that we have studied so far, right? We have studied so far. So if you take a look at the typical circuit, let's say a typical RLC circuit. This is just a random example, okay, random example. So this is similar to one of the homework problems, right? You have a resistor, inductor, capacitor in a circuit. If we isolate this and remove the source from the left side, we can say that the 2 terminals where the source was connected comprise a set of terminals plus and minus for the source. So 2 terminals put together comprise 1 port. And so we refer to this as the input port. Okay, input port. And on the output side, typically we might measure the output across the component here, right? So if we are measuring the voltage, or perhaps we might be measuring the current, we would again take this set of terminals on the output side, isolate it, and we call it the output port. Okay, so it's the same circuits that we have dealt with so far. The only thing is we are going to look at those circuits a little bit differently. So on the left side, where we have the source, we'll say it is a input port. On the right side, we'll say it is the output port. And each of these ports is comprised of two terminals, one for positive, one for negative. And so we refer to them as a two-terminal, two-port network. Okay, two-terminal, two-port network. Hence the phrase two-port networks. Now, in electrical engineering, the E majors have to take a class where there's an entire chapter devoted to two-port networks. We obviously are not going to do, all of that. But the filter functions by taking the incoming input signal. The incoming input signal can be comprised of hundreds of thousands of different signals. When I say signal, I'm talking about voltages and currents. Signal is simply just an input parameter that's coming in. Okay, so there are hundreds of thousands of input signals coming in. A filter is going to block most of those and only going to allow certain category of signals to pass through. Okay, so we want to know how the output is going to change with respect to the input. Okay, we want to know how the output is going to change with respect to the input. Hold on. And in order to do that, in order to quantify that change, we come up with a new quantity. H of F. H of F. I would like to say it was named after me because I invented it, but that's not true. H of F is simply the ratio of V out to V in. V out to V in. Okay. So ratio of V out to V in. It basically describes how the output is going to change with respect to the input. Okay. It's also telling you how the input is being transferred to the output, and hence the name transfer function. Okay. So it's describing how the input is transferred to the output. Hence the name transfer function. So simply put, it's the ratio of output to input. And what do you see about this notation? What does this uppercase V along with that thick shaded line on the left, what does it remind you of? Someone? Yes, someone? No one? Chapter 5, it's a phasor. It's a phasor. And so V out and V in are phasors, and therefore H of F is also a complex quantity represented by complex numbers. It has both magnitude and it has phase. So H of F, the transfer function, has magnitude and it has phase. Phase angle. It's a complex quantity. What are the units? Anyone?
It's unitless.
It's unitless. It's a ratio of voltages, right? The ratio of the two quantities. So unitless. There's no units. It's simply describing how the input is being transferred to the output. If this was an amplifier, for instance, the transfer function would be describing the gain of the amplifier, right? How much power or how much value is that input signal gaining when it gets to the output. So in terms for this chapter, we are studying filters. And so the transfer function is going to describe the function of the filter. We could take a look at the transfer function and we'd be able to state what kind of filter it is. So before we get into that, just want to briefly explain how a filter might work. You would have an incoming signal. That incoming signal is comprised of multiple numerous components. In this example, it's comprised only of two. It's only comprised of two components, just to keep it simple. So effectively, the filter will work like this. The amplitude and the phase of each component is changed by separating it out. In reality, of course, it's not separating out. This is just an explanation. Okay. So if you have a filter, think of it as it's separating out the two components. So in this case, the input signal has two components, one on the left, the other one on the right. You can see both of them have sinusoidal shapes, right? So it's a sinusoidal signal. Then, depending on the function of that filter, one signal is either blocked and the other signal is allowed to pass through. So if you look on the left, the signal one right here is actually become larger, right? It's larger in magnitude. So some gain was applied to that component, whereas signal two on the left, on the right, is now smaller. So the signal on the left is amplified, the signal on the right is attenuated. Okay, this is amplified, the other one is attenuated or reduced. In electrical engineering, if you ever read the terms attenuation, it is the exact opposite or an antonym of amplification. Okay, amplification is providing more gain or more value to the signal. Attenuation is reducing the value of the signal. Complete opposites of each other. Okay, so the filter would provide gain to some signals and attenuate some other signals. And then you combine the signal back and at the output. So this is your input signal. And now this is your output that has changed. Okay. It's important to note that the filter will affect both the magnitude as well as the phase. Okay, so as the magnitude is changed, the phase of the output is also changed. So again, this is an approximation of how a filter would actually work. All right, any questions? Any questions at all? Yes. Separating it out. So any signal, meaning any kind of AC waveform, time varying AC waveform, whether it's a square wave, rectangular wave, arbitrary, doesn't really matter what kind of shape it is. We can use mathematical techniques and show that each waveform can be broken down into like numerous components, and each one of them is a sinusoidal waveform. So this is kind of like, this is not exactly what the filter does. This is just showing you how the filter affects separate components. So filter is not actually separating it out like that. It's not separating it out. This is just for explanation purposes. Like an actual signal will not just have two components, it would have hundreds of thousands of components. When I say input, like if I hold my phone up here right now, the phone is receiving signal from, like, say, Verizon, AT&T, Sprint, T-Mobile, FM radio, AM radio, television signals. It's receiving all the signals in here, right? Depending on the functionality of the phone, depending on the filter, it'll block out all of those signals and only allow one particular signal to go in. Okay, so when I say it's separating it out, that's not really what is happening. It's not actually separating it out. What it will actually do is it will block out certain components. This is just for explanation purposes on how, if we take a signal how it affects it differently. Okay, so if it's made up of multiple components, it's going to affect certain components differently than others. Okay, and you will see how we're actually going to apply this in a circuit. Okay, let's see. So this is part of the first homework of filters, which is 18 transfer function. No, 17. Can't remember the number. Anyway, that first this chapter has 3 homework assignments. The first one only has like 2 problems. The problems are similar to this one. Okay, here it's asking you for the frequency response of the output. I mean, frequency response of the input. Sorry, let me take it back. The frequency response of a particular circuit is presented in graphical form. Okay, it's presented in graphical form. So this particular method is used to solve graphically. You would obtain the data from the charts that are provided to you. Okay, so the circuit is not provided, only graphical representation of the transfer function is provided. Okay, only graphical representation. So on the left here, we have the magnitude. On the right, we have the phase of the transfer function. We are not told what kind of circuit it is. We don't really care what kind of circuit it is. We only need to, what we need to do is just determine what the output would be given any particular input. Okay, given any particular input. So let me bring up a specific question. Let's see. So again, to recap, when you're faced with such a question, graphical representation of h of f. So we take a look at the frequency that we need to find. If we need to find V out of t, when V in of t has an omega of 2000 pi, omega of 2000 pi gives us f at 1000. At 1000 hertz, magnitude h of f is 3, phase is 30 degrees. So we can write h of 1000 as 3 angle 30. H of f is V out over V in. So V out is h of f times V in. We write the phasor for V in, which is 2 angle 40. V out is simply 3 times 2, magnitude of 6. And phase angle 30 plus 40, so 70. So 6 with a phase of 70 degrees. Final answer, V out of t has to be in time domain. And so we have to write 6 cos of 2000 pi t plus 70 degrees and volts. Questions? Any questions? Okay. Second example. And this is, so let's do example 2. V in of t now comprises of 3 components. And those 3 components are 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t I'm gonna have to move this. Plus, no, minus 70 degrees. T minus 70 degrees. Okay. So now it has 3 components. V in of t is comprised of 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t minus 70. First things first, there are 3 separate components. Can we combine them? The answer is no. The frequency for all is different, so we can't. So we just separate it out into 3 different components. And so what I'm going to do is I will say there's V in 1 of t, V in 2 of t, and V in 3 of t. The first component is simply 3 volts. What is the frequency? 0. It's simply a DC line. It's a flat DC line, right? Constant voltage. So here, F is 0 hertz. Second, V in of t is 2 cos of 2000 pi t. Frequency F is 2000 pi divided by 2 pi. And so F is 1000. And then the third one is cos of 4000 pi t minus 70 degrees. So F is 4000 pi divided by 2 pi gives me 2000 hertz. Okay, 2000 hertz. So 0, 1000, and 2000. So then we go up to our chart and we find H of 0. H of 0 is 4 with an angle of 0. Right? 4 with an angle of 0. So H of 0 is a magnitude of 4, angle of 0. So I'm just going to write 4. H of 1000, we already found in example 1. 3 angle 30. And H of 2000, let's see what it is. At 2000, magnitude of 2 and a phase angle of 60. Okay, magnitude of 2, phase angle of 60. So 2 with angle of 60. Make sense, right? And that's it. And then from that point, this point on, you just proceed in the same manner. V out is H of F times V in. Okay. So I'm going to leave that as student practice. And I'll give you the final answer. Final answer is going to be V out of t should be equal to, what should it be equal to? 12 plus 6 cos of 2000 pi t plus 30 degrees plus 2 cos of 4000 pi t minus 10 degrees and volts. That's the final answer. So in the exam, if you see something like this, the first thing you should check is whether the frequencies can be combined or not. If the frequencies are, if the components can be combined or not. If the frequencies are not the same, we cannot combine them. The frequencies must be the same in order to combine. So if they cannot be combined, we just leave the answer as it is, has multiple components. You can be sure I'll sneak it into one of the questions. So be on the lookout for that. Okay. All right, any questions? So this is, I think, the first homework, transfer function in chapter 6. I think there's 2 problems and both of them are similar to this one. Okay. So get those done as soon as possible. Do not wait. Okay, so that was a simple, straightforward explanation for transfer function and how it could, how we can predict the output of a circuit without knowing what the circuit is or what it actually does. We can simply look at the graphical representation of the transfer function, and then we can determine the output. Then let's actually get into the filters. Filter circuits uses the properties of an inductor and a capacitor, where their impedance is dependent on the frequency, right? We saw in chapter 5, Impedance of a inductor is j omega L. Impedance for a capacitor is 1 over j omega C. So based on that, we create this table, which I call the handy dandy table. The handy dandy table is basically displaying how a capacitor or an inductor can be approximated at extremely low and extremely high frequencies. So at extremely low frequencies, we are saying that F or omega is tending towards 0 hertz, basically DC, right? For DC. In extremely high frequencies, F or omega tends towards infinity. So what happens? Remember, inductor j omega L, j omega L. So, or j 2 pi FL. So if F is equal to 0, ZL is 0, right? F is equal to 0, ZL is equal to 0, F is equal to infinity, ZL is infinity. So at extremely low frequencies, inductor behaves like a short circuit, or SC, which we already know this from chapter 3. If you apply a DC voltage or current to an inductor, after it reaches steady state, it behaves like a short circuit. Remember that from chapter 3? And capacitor, when it's fully charged, meaning if you apply DC to a capacitor, capacitor behaves like an open circuit. So extremely low frequencies, we are saying F is equal to 0, meaning we're applying DC for all intents and purposes. Constant value. Capacitor behaves like an open circuit, inductor behaves like a short circuit. At high frequencies, capacitor behaves exactly the opposite. ZC is 1 over j omega C, or 1 over j 2 pi FC, inversely proportional to the frequency. So when frequency is 0, ZC is infinite. When F is infinite, ZC is equal to 0. These properties are very helpful in building filter circuits because they behave opposite of each other. We can use them to block out certain values of low frequencies and allow only high frequency to pass through, or we can allow it to block high frequencies and only allow low frequencies to pass through. Does the table make sense? Right? This first prediction at the low frequencies is something we've already seen in chapter 3. Right? We've already seen that in chapter 3. And then the second column on the right, well, we've seen that in chapter 5. The only thing is we can model the capacitor and the inductor with an open circuit or a short circuit. And this table or this behavior will allow us to predict or do a quick analysis of any kind of filter circuit, right? Quick analysis of any kind of filter circuit. Any questions before I move on? Any questions at all? Okay, so the different kinds of filters we're going to study are based on the circuit or the component. If there's a capacitor in the circuit, we refer to it as a RC filter. If there is a if there's an inductor in the circuit, we refer to it as a RL filter. So we have RC and RL filters. It's one energy storage component. So a first order differential equation, hence a first order circuit, and hence a first order filter. So we say that RC and RL filters are first order filters. And depending on the circuit configuration, or more importantly, where we take the output from, we can have, or we can create low pass filters and high pass filters. And it's a 2x2 cross matrix. So we can have a RC low pass filter and high pass filter. This table might be confusing. but it is a cross matrix for both. And for RL, we can have a low pass and high pass. Okay. No, no, no. It's not as if it's RC. I know the table is is written in such a way that it implies that an RC low pass, but that's that's what I wanted to explain. So you can have both RC low pass and high pass, and you can have RL low pass and high pass. And if you combine both of them together, you get what is known as a band pass or a band reject filter. Band pass or band reject. Okay. Pretty much all filters that we use in everyday life are band pass filters because it allows a certain band of frequencies to go through, right? Or one single particular frequency to pass through. So band pass filters or band reject filters are typically second order circuits. So it's a second order filter. We will look at the band pass, especially the resonant circuits. The resonant circuits have both inductors and capacitors, R, L, and C, and so they will be band pass filters. So let's take a, how much time do I have? Let's see, 9 minutes. Okay, this time. Let's take a look at the first one, RC low pass. Okay. Now again, I'm going to move what we did earlier, right? I'm going to split the left side. And if I was just looking at it as at a box or a sealed box, that sealed box has an input on the left and an output on the right. But this shows you the circuit formation of a RC, circuit layout of a RC low pass filter. It basically is a resistor in series with a capacitor. That's all it is. And you're applying a input to that series combination. And you're taking the output across the capacitor. Output across the capacitor. Now, there is a derivation in the book for non-E major classes. I typically do not do the derivation, but I'll explain the steps. It's a series connection and you're applying V in, right? So if this were two impedances in series, we can combine them into one single impedance, RE or ZEQ, right? So it would be R plus ZC, R plus ZC. Then you find the total current I that is going to the circuit, or you apply voltage division and simply find the output across that capacitor. And that's it. As straightforward as that. So the derivation is basically one step R and ZC, and you have phasor or V in. You simply find V out by applying voltage division. So V out would be V in times ZC divided by R plus ZC. And then when we take V out over V in to determine the transfer function, we come up with this equation, which is 1 over 1 plus J F over FB. There are some terms in there that are manipulated to actually put it in this form. Okay. FB is defined as the break frequency or the transition frequency. It is also known as the cutoff frequency. Okay, cutoff frequency. So in other classes, you might, or other books, you might come across the term FC. So FC stands for cutoff. The B stands for break. So FB is break frequency. FC is cut off frequency. And they are synonyms of each other. They are exactly the same. They mean the exact same thing. Mathematically, FB is described as 1 over 2 pi RC. 1 over 2 pi RC. 1 over 2 pi RC. So then let's talk about what it actually means. This is just quantitative. Let's have a qualitative discussion, right? Qualitative discussion. So again, as I said, determining V out is rather straightforward. You have a series connection of two components. You apply voltage division. You find the voltage across that capacitor, and you get V out. V out over V in gives you H of F. H of F for a low pass filter. And you will see in a few slides next class, whether it's a low pass, whether it's made out of RC or RL, a low pass filter will have the exact same transfer function. So you get the equation 1 over 1 plus JF over FP. It's H of F, meaning F is the variable, right? F is the variable. The incoming signal can take multiple different values, right? We just talked about there are so many other signals that are coming into the circuit, right? H of F describes how the circuit is going to behave or how it is going to treat every single incoming signal based on its value of F, based on the frequency. Okay, based on the frequency. FB is fixed. As a circuit designer, you can fix it by choosing values of R and C. Okay, FB is fixed. 1 over 2 pi RC. So let's see what happens. There's about 3 minutes left. Let's see what happens when we plot this for an ideal filter. Actually, instead of taking H of F, I'm going to say V out on the y-axis. Okay. Right now we'll leave magnitude on the side, but simple plot of how V out changes with respect to frequency. What do we expect? If it's low pass, it should allow low frequencies to pass through, and it should block certain high frequencies, right? So the transition point is FB or FC. That transition point is FP. So depending on the value of R and C, we have a transition point between the passing of the frequencies and blocking of the frequency signals. And so because there's a transition point, we say frequencies below, it's a low pass filter. So frequencies that are lower than FB are allowed to pass through, meaning they will have V out will have a magnitude or a value exactly equal to V in, right? The filter should not affect the output at all. V out should be equal to V in. And any components that have frequencies higher than FB should be blocked. So this would be known as the pass band, and this would be known as the block band, no pass zone. Now, in real life, real filters, we can never have a straight, like, it's being passed and then completely all the way to zero. V out will never go completely to zero. It'll be a slow transition. So it'll be something like this. It'll be something, I made a hash of it, but it should be something like this. Gentle slope. Okay, gentle slope. So this will be kind of like an ideal. This would be real or practical. Okay, there's a slope. So that slope, because it is a gentle slope, where is the transition point? Right? We don't know where the transition point is, right? The transition point can be given by that equation right there, F over FP. So here, the value of V out is going to drop to 70% of V in. And at that point, right here at FB, you can see that some values, I mean, some frequencies that are on the left side and on the right side will still be passing through. It'll still have, so if you have a frequency that is FB plus 1 hertz or FB minus 1 hertz, if it's FB plus 1, it's not as if it's going to be completely blocked. It is still passing through with some value, right? V out for FB plus 1 is still not 0, right? Oh yeah, I was going to explain why and how. So if you look at the transfer function, h of f is 1 over 1 plus j f or fb. H of f is a complex quantity. It has magnitude as well as phase. When we take the magnitude of h of f, and I have equations for magnitude later on in this chapter, it comes out to be 1 over root of 1 plus f over fb square. So if f is equal to fb, meaning the incoming frequency, the incoming input signal has a frequency that is exactly equal to fb, what happens? When f becomes equal to fb, the magnitude of h of f falls to 1 over root 2. 1 over root 2. So V out over V in is 1 over root 2. So V out is 0.707 times V in when F becomes equal to FB, and hence 70%. So when we have a graph or a chart of V out versus F, we are plotting all the input signals that are coming in. We can have a abrupt transition from from V out max all the way to 0. And so the transition point is where the incoming signal is equal to FB and V out falls to 70% of the maximum value of V in. So V in was 1 volt, V out at that point would only be 0.7 volts. And at that point, we say that that's the transition point between low pass and high pass. So, already went way over time. So let me stop right here. We'll pick up here on Monday. A quiz on Monday, most likely AC power. I probably won't have power factor correction in there. But again, I'll send out details as usual sometime later today. All right, have a good weekend and I'll see you on Monday.